Hello. So I hope everything is going on very well with you. I will grade your test over the weekend, and I post the result and the solution for you. So what we're going to do, the next target is chapter 4. It's a very dense chapter. So I'm going to give you some idea of the fundamentals of this chapter, section 4.1, 4.2, very important sections to give you an idea what's going on. Okay, so what we did so far, we introduced this collection of matrices, and we introduced some operations, especially addition and the scalar multiplication. And we proved that those, addition behave like addition with the numbers, it's commutative, associative. There is a zero element. Okay, every element or every matrix would have an opposite, and it seems to be behaving like the set of real numbers. Then in chapter 3, we we brought a little bit of geometry. We extend the set of real numbers into the set of points in R2, and then set of vectors in R3, R4, and the Rn. So we extend a notion of adding addition for the vectors, the scalar multiplication, and we just show that this system again Rn will have all the famous property of in geometry, the property that you have in R2. So we can extend it to the R3 and then to the Rn. So that is the kind of classic examples that we have a model. In our model, there are some objects. Those objects can be so far matrices, they can be vectors, and then we introduce two operations. The operations of addition, we call it vector addition, and the scalar multiplication. So what we're going to do is, why we just dealing with the vectors, or why we just dealing with the matrices? So why not? Let's bring everything into the general format. So what we're going to do is, we are going to introduce a collection of objects. Those objects, we call them vectors. Okay, those objects can be functions, can be matrices, can be numbers, can be vectors. Okay, whatever you like, but we refer to them as vectors. So we have a collection, a set of objects, a set of vectors, but we are going to introduce two operations on this set. One operation is addition. We call it addition, okay? It's like additions. We call it vector additions. And the other operation is a scalar multiplication. A scalar multiplication means we get a number and we multiply by the members of the set. If you multiply a member of the set by a scalar and the result's going to be in your set, we say this set is closed under scalar multiplications. Then we arrange that the one that we call it addition that follows the addition properties, like commutative property, having a zero element, associative property, etc. If your sets of collection with the operation of addition and scalar multiplication behave nicely, this set is going to be called a vector space. So the vector space is the abstract of all the other things that we talk about it so far. So why not? We work with the vector spaces, and if you feel that we need an example, quickly we go down to the R2, R3, Rn, etc. So I'm going to give you introduction to the vector space. We introduce the vector space, then we extend everything, and things getting so nicely. It's a romantic part of the course. You don't need to use the matrices, okay? You don't need to use vectors. You can do whatever you like. It's going to be quite interesting one. So these are going to be the properties of these sections. Okay, a number of the definition to work out. 4.1, 4.2, very important one, and we take it from there. Okay, so let's go and just give you the definitions that we're going to have. It's very important to understand the foundation of this concept. And from there, we can go to the building up theorems and eventually applications. This is going to be what we're going to do, okay? So 4.1, we go out of the classic case. We go to the vector spaces. Okay, so it's going to be the introduction of the what is vector spaces. Vector space, a collection of objects with two operations. That's it. So there you are. Let V be that set, be a set, a collection of whatever you like. A set on which or in which two operations are defined. Two operations. Okay, operation, we call it addition for the vector addition, and the other is going to be a scalar multiplications. Okay, so there you are, vector addition, okay, vector addition and a scalar multiplication, numbers, okay, scalar multiplication. So we have a set V and these two operations that is going to be, so V is a set of be a set on which two operations, the addition and the scalar multiplication, are going to be defined such that the following condition satisfy. The condition is like the condition that you have for addition. You see, this is it. So you have that there. The first thing to do is if we get, okay, this space must be closed under addition. So this means if you pick two elements, you see the first one is if U and V are in V, then U plus V is also in V. So this means this is closed under addition, okay? If you add two members of the vector of the set, you get a member of a set. Okay, that's the first one. The second one is a scalar multiplication. If U is in V, a vector, a member, and alpha is a real number, is a scalar 2, 3, 4, 5, 6, then alpha times U is in V. So this means this is closed under this operation. Okay, if you multiply a member by 2, if you like, twice of the member is also a member of the set. So the set is closed under addition. They have the same kind of members, if you like. You know that you can add only the like terms, if you like. And so if this is going to be the second case, then the operations that we have, when you say addition, you mean it. You mean it means they are going to be commutative. Okay, commutative. Whatever addition you define, it must satisfy this condition. It must be associative. So if you have three members, okay, three members, you can add them as you like. So this is commutative. This is associative. You must have a member that we call it zero member. Okay, so there is a member, there is a zero in V. Okay, there is going to be a member that we call it, okay, such that 0 plus V is going to be equal to the V. So you have to give us this member. So your vector space would have a zero element. As soon as we get the zero element, we are going to have the opposite or the additive inverse of the members. Okay, so if again U is in V, then there is a vector. There is a vector okay, a vector, we call it negative u in V, such that, okay, such that u plus a negative u is going to be equal to the zero. So you should have something that similar to the zero. We call it zero vector. It's a zero vector if it satisfies this condition. So every member in your set would have an opposite. Opposite. It's very much like the addition. Okay. Then the other property are going to be property of the scalars, numbers. If you multiply a number by the sum of two vector, you can distribute it. Okay, you must have this condition. Okay, and you should have this condition that if you have alpha and beta, both of them are a scalar. If you multiply by u, so that give you alpha u plus beta u. Okay, these are all the scalar property. The other one is like if you have the alpha times beta times u, 2 times 3 times u, you can multiply both of them together. So it's going to be, okay, it's like alpha beta, then the u. Okay, and the last one is 1 as a scalar, okay, as a number, and if you multiply a scalar multiplication by the u, so that give you u2. Okay, so if you have okay, so if your V is going to be a collection of sets, okay, a collection of sets that satisfy all these equations, then okay, then V with these operation that we talk about it, okay, the set V with the operation of addition and the scalar multiplication that we define, all of them together, okay, all of them together, or just V is called, okay, is called a vector space. Okay, a vector space. So that's going to be the case that we are going to have. So the vector space would consist of two parts. One part is a collection of objects. The other part is the operation. You must be able to define two operations on it: addition and scalar multiplication. Addition and scalar multiplication with something natural. Okay, these are going to be natural one. Some of them you can drop some of them. Okay, and prove the other one. But computative, associative, this type of operation, you must have it. So if you have a collection of objects with these two operations and it satisfies this condition, then this collection is going to be called a vector space. Okay, and if you want to have example, whatever you did so far, they were vector spaces. You see, example, the most recent one, Rn. Okay, remember the Rn, n-dimensional Euclidean n-dimensional space. Rn, you have to tell us what type of operation. With the operation of, with the standard vector addition, vector addition. A standard vector addition means when you want to add two vectors, remember, we add the coordinates together, coordinate wise, if you like. So Rn with the standard addition, because we already proved that it's follow all those property, and the scalar multiplication. And you have to tell us these two operations. Okay, scalar multiplication, okay, is a vector space, is a vector space. Very classic result. That's why we just check a few sections of that previous okay chapter, just to make sure R is going to be just vector space. R2 sets of order pairs is the vector space. R3 is a vector space. So we introduce the operation, how we're going to add those vectors together We add them together by adding the coordinates together. Okay, so this is going to be one classic example. Okay, the other one that we did so far is just what? Matrices. If you have a collection of all m by n matrices, you know that you can add them together, and addition of the matrices would follow all these properties. A scalar multiplication, you can multiply a matrix by a number. You know how to do it. You multiply all the entries. So the result's going to be a matrix again. So the second example that we have, everything you did so far is a vector space. So let's have another one. Another one is the collection, the set of, there you are, the set of all, okay, all m by n matrices. Okay, all m by n matrices, you have to tell us. We say that, oh, with matrix addition, we know what does it mean. When you want to add the matrices, remember, you add the corresponding entries, and a scalar multiplication, and a scalar multiplication. You see, you have to tell us which type of operation. Okay, a scalar multiplication, the usual one. Multiplication is a vector space. Is a vector space. Okay, because we have all the other conditions. What is the zero matrix? Okay, zero element, zero vector. It's a matrix with all entry zeros. Okay, you know that the additions is, what is that? It's commutative, associative. We proved all these properties before. Okay, so as you can see, we covered everything. Everything we did so far. Then how about this one? Polynomials. Let's get something from. Okay, let's bring something from calculus. In calculus, you can have. How about set of all continuous function? You see the set of all continuous function continuous function. Let's say on the closed interval of a comma b. See, with the usual addition of a function, we call it with pointwise. Okay, pointwise operations. Pointwise operations is a vector space. Vector space. Pointwise means if you add two functions, remember f plus g is f of x plus g of x. At any point is the way we multiply. So if you have two continuous function, the sum of two continuous function is a continuous function. So it's closed under addition. If you have a continuous function, if you multiply by a scalar, you multiply by 2, 3, 4, the result is a continuous function. So we have the operations, and all the other property would satisfy quickly. The important part is the first one. Remember, the sum of two elements, two members of your set must be a member of the set again. So the sum of two continuous function is continuous. And if you multiply a continuous function by a number, the result is continuous. The rest of the operation is like addition. You get it, get it right away. Okay, so you see, we're building the calculus. You may think that, oh, everything is nice, but this example, this is the one we're going to use it from time to time. Okay, from time to time, we use this one. We are going to use polynomials. We identify the polynomials with their degrees. Okay, so if you consider the set of, you see, the set of all polynomials, okay, polynomials of the, okay, set of polynomials of these are going to be the one. You see, we are going to consider the set of polynomials of degrees, okay, or with the degrees at most 2. Set of all polynomials, okay, the set of all polynomials of the form, set of all polynomials of degrees, okay, of degrees 2 or less. 2 or less. 2 or less, we say that the polynomials of degrees at most 2. At most 2. At most 2 means 2 or less. 2 or less. Okay, the set of polynomials, okay, of degrees 2 or less is a vector space with the usual operation. Okay, with a standard operation. It's a function. So standard operation means addition. Okay, the point was like the function. Okay, is a vector space. Is a vector space. Okay, this is going to be a vector spaces. So this means you get the polynomials is they are going to be quadratic or linear if you like. This is going to be the one. But you got to be careful if you have the collection of all polynomials. Look at this one. We're going to use this one as a source of a counterexample. So if they ask you the set of all polynomials, okay, a set of all polynomials of the second degrees, okay, the set of all second degree polynomials, if you like, all polynomials, all, let's say, all second quadratic, okay, second degree polynomials, and this is not a vector space. Okay, is not going to be a vector space. When you're dealing with the polynomial, you can say at most 2. At most 2 means 2 or less. We are going to have this one quite a lot. At most 3. This means 3 or less. Not exactly. So why not exactly? Because I can give you 2 polynomials of the second degree that if you add them together, the result is not going to be a second degree. Remember, if it's going to be vector space, it's meant to be closed under the addition. So this is how we're going to reject it. You say that the note that, okay, note that if you consider 2 polynomials, you see, if p of x is going to be x squared, and this is 1, and the other one is going to be, I give you q of x equal to the negative x squared. Okay, negative x squared plus 2x plus 3. If you add them together, you see both of them are in your set. So their sum must be in the set too. But if you add them together, we get a px plus qx, which is going to be x squared. Okay, if you add them together, this is it. We get x squared minus x squared plus 2x plus 3. You see these two will cancel out. We get a 2x plus 3. You see the sum is not a second degree. A second degree. Okay, a polynomial. So you must have at most, because you know that the first condition for the vector space is if you get 2 members, you add them together, the result must be inside the space. In this case, it is not. Okay, so these are going to be the situation you're going to have for the vector spaces. So you have, some would be given to you, and they ask you to check to see if they're going to be vector space or not. You just check to see if you can, if you can reject it if you like. Check this one first. Okay, check this one first. Give you another one. to get the idea of where you won't get it. You have some similar problem in your book. Just wanted to see. You see, suppose we introduce the v equal to the R2. You see two-dimensional, if you consider with the usual operations, if you add two vectors, you add the vectors by adding the coordinates, it's going to be a vector space. But sometimes they may introduce a new operation on it, okay? So suppose v equal to the R squared, okay, with the following, this is it. Okay, this is going to be the case with the standard addition, with the standard vector addition, and the following scalar multiplication, and the following. They may give you something different. Following a scalar multiplication. You have some of them in your book. Okay, they give you this scalar multiplication. They say if you have C is going to be a scalar, or K is going to be the scalar if you want to multiply by a member of your set. Okay, the usual one is you write K x1, K x2, but they give you this one is the K x1, comma 0. Okay, so that's a suggestion. So you have a collection of points into the all the points in the two-dimensional space are 2. Addition is as usual. You just add the coordinates together. But scalar multiplication, they introduce this one. Now they ask you if this V is going to be a vector space. The answer is no. If this is going to be the case, then V is not a vector space. Not a vector space. So you have to reject it. You have to give us a reason why you reject this one. And for the addition, nothing to worry about. You have to reject this one. Remember, if you multiply a vector by the scalar, the result must be in your set again. Okay, the result must be in your set. Let's see how we're going to reject this one for you. To reject that, we are going to show you that. You see, note that this is going to be our rejection. If you put k equal to the 1, so we get the 1 as a scalar, and multiply by this vector. You see, multiply by 1, 1. Multiply by 1, 1. Okay? On one hand, according to the definition that we gave you, since you multiply by 1, this must be the same thing. Okay? But if you use this definition, what's going to be the result? You see? You say, oh, but if I want to use this definition, it's a 1 times 1, 1. According to this definition, must be what? Kx1. So it's going to be equal to the Kx1, 1 times 1, which is equal to the 1, and the comma what? Comma 0, because the definition that we're going to have. Now look at this one. So 1 times 1 times 1, because 1 multiplied by anything is identical. But in this operation, if you multiply them together, that give you 1, 0. So this means this is going to be a contradiction, okay? So this is going to be a contradiction because that will tell you that 1, 1 must be equal to the 1, 0, which is not going to be possible to get these numbers. Okay, so this is not going to be a vector space because it's not closed under the scalar multiplications. Okay, so that's going to be the way we are going to see it. Okay, so that is the notion of the vector space. So a vector space is going to be a collection of objects that collection of objects must have, okay, you must have an addition and a scalar multiplication. In particular, you must have a zero element, if you like. Okay, you should have something that we call it zero vector. Then you multiply any vector by the zero, the result must be zero. Okay, so that is going to be a vector space. Now, what we are going to do, you see the vector space is going to be very big to work with, okay? So it's going to be very big. It's like, you know, if you have a set of real numbers, then you have a sum collection, sub collection of the natural numbers, integers, etc. So what we're going to do, and sometimes we may like to shrink this one. Okay, so we have a set. I give you quite a lot of vector spaces over here, but in order to investigate the vector space, you see the vector space is very big. So in order to get the idea of a vector space, we are going to pick a collection of these vector spaces. Okay, a collection is going to be a collection of the members. So the question is, if you pick a collection of the members of the vector space, yeah, so you have a smaller set, you didn't got the addition and scalar multiplication on the original sets. But if, you see in the original set, if you pick two vectors, you add them together, you are going to be dropping into the vector space. Now, if you get a sub collection, if you get a subset, if you get a subset of a vector space with the same property means if you add two members of this subset, again, you get a member in your set. In that case, that sub collection is going to be called a subspace. So the subspace is just a subset, subcollection of a vector space such that that subcollection by itself is a new vector space. And that's very important for us, very important, because the vector space is too big. So in order to investigate it, we go with the subspaces. So that will take us to the section 4.2 quickly. Okay, and it's very dense section. 4.2, what is subspaces? And your first question starts from here. We give you something and we ask you to check. Okay, so what is going to be subspaces? Subspaces. Vector space, very good, very big. We pick a subcollection of the vector space if they have the same properties as the original one, means if you add two vectors, you get the result inside the subspace. And if you do the scalar multiplication, the same thing, say, oh, it is a subspace. Okay, so there you are. Suppose you have the big one. Okay, this is it. Suppose V is a vector space, the big one is a vector space. Okay, V is. So this means what? This means you have two operations, addition and scalar multiplications. Now, a non-empty, there must be something in it. Okay, a non-empty, a set of one element at least. A non-empty subset, subcollection, subset of V. Subset of V, okay, is going to be called, okay, it's called a subspace, okay, if itself, by itself, okay, when, okay, sorry, a non-empty, I should give us a name. Okay, suppose V is a vector space, a non-empty subset, okay, let's say a W of V, a smaller one, of V is called a subspace when W, this new one. So when W is going to be, is a vector space, it's in, you know, it's going to be a vector space by itself with the same operation, and there the same operation, and there okay, and there the operations, and there the operations of addition, of addition, addition, and scalar multiplication, scalar multiplication, okay, in V. You see, you already got these operations on the V because the V is the big one. If you pick a sub-collection of the V, a smaller set, you call it W. With the same operation, addition and scalar multiplication that you have already on the big one. Okay? If these new sets is closed under this operation, close means if you pick two elements in W, you add them together, the result is in W. How are we going to add it? Addition is like the one that you define on the V. So if two members of the W, the sum of two members of the W is going to be in W, and the scalar multiplication of any member of W is in W, then W is going to be a subspace. Because when you add two vectors, the sum of those two vectors is always in V, the big one, because V is a vector space. But if it is, if you take two vectors from W, the sum is also in W. And if you take a scalar multiplication of a vector of W, the result is going to be in W. W is going to be called a subspace. So by itself, it's a vector space. But since it's the smaller one, we call it a subspace. Okay, so let's finish it. So when W is going to be vector space, and there are operations of addition and multiplication from V. So what is going to be the case? So W is a subspace, is going to be a subspace of V if satisfy two conditions. Okay, if the first condition is going to be, okay, if U and V vectors are in W, then U plus V is also in W. It's closed under addition. The second one, if U is in, okay, is in W, and alpha, or the K, alpha is a scalar, then alpha times U is in W. Okay, basically it must be closed under, okay, it must be closed under vector addition and the, okay, scalar multiplications. Okay, so this means you forget about the V. Stay in the W, because W do the same thing for you. And that's your main job to check for us. Okay, there's going to be one question that will be given to you. We are going to give you a collection of these subsets, if you like. Then you have to tell us whether you should be able to prove it for us. Okay, so you get quite a lot in this case, and your next practice quiz. So there you are. So suppose example number one. Number one, suppose this is W. Suppose W is going to be a collection of points in three-dimensional x1, 0, x3. It's going to be all the vectors whose middle middle coordinates or component is going to be 0. It is going to be W, of course, when x1 and x3 are real numbers, are going to be real, okay, real numbers. So this is going to be the sets of your point. Now we want to prove that this is going to be what? Is going to be a subspace. This is a subspace. Is a subspace of, okay, it is going to be a subspace of R3 with a standard operation. You have to give us the operation with the standard operations. If you want, you have to prove it. Okay, this is it. So what is going to be the solution or the proof? There you are. You have to prove those two conditions that we talk about it. Okay, so if you like solution, pick two elements in W. Show that if you add them together, you get a similar one. Okay, and pick two members. You see the first condition is going to be, the first condition, you say that if you have x1, comma 0, x3, this is one member, and y1, comma 0, y3 are in W. Add them together, show that there is sum. You see x1, comma 0, x3. If you add it to the y1, 0, y3, what's going to be the result? Component by component. So that gives you x1 plus y1, comma 0, x3 plus y3. You see, that gives you exactly the same kind of members. So a member is in W if you see, if the middle component is 0. So this is in W, is in W. Okay, so it's closed under addition. And the second condition, okay, a scalar multiplication, alpha times x1, 0, x3. You know that this is going to be what? Alpha x1, the middle one would be 0, and the alpha x3. You see, if you multiply a number, if you multiply a vector in W by a number, the result is also the same kind. So this is in W. So two conditions satisfy, W is a subspace. Okay, it's going to be a subspace of R3. See, this is the way you prove. You have to prove those two conditions that we talk about it. Close under addition, if you get two members in W, the result is in W. A scalar multiplication, if you get a member in W, you multiply by 2, 3, 4, 5, 6, the result is going to be again in the, in the set. Okay, so this is going to be one. Give you another one. You have quite a lot. Assignment of this section, quite a lot. And we give a collection in your next quiz. This second one is interesting. Suppose W is, remember, symmetric matrices. A matrix is symmetric if its transpose is the same as the matrix. So suppose we get all these collection. Suppose W is going to be the set, the collection, the set of all 2 by 2 matrices, 2 by 2 symmetric. Okay, symmetric matrices. Symmetric matrices. Okay, if this is going to be the case, then W is a subspace. Is a subspace. Say it's a subspace of M2 by 2. M2 by 2 means all the 2 by 2 matrices. Okay, this is all the 2 by 2 matrices. W is just the symmetric one. Okay, so basically this is W. You see the W is the set of matrices with the condition that the A transpose is the same as A. That is W. So to show it, you need to show 2 points for S. Pick 2 members of the W and show that the sum is also a member of the W. So the solution is going to be condition 1 that you want to prove. You are going to suppose 2 members. Suppose, let's say A1 and A2 are in W. So this means A1 transpose is the same as the A1. A2 transpose is the same as the A2. Now how about their sum? So A1 plus A2 transpose, you know that this is going to be A1 transpose plus A2 transpose. But the A1 transpose, they are symmetric. So that give A1 plus A2. Okay, so this means A1 plus A2 are in W. So this means if you pick 2 members in the W, they are both symmetric. If you add them together, the result is also symmetric. So it's close under addition. Okay, a scalar multiplication, you have to prove both of them when you do the problems. Okay, a scalar multiplication, and that's it. If you know that, note that. If you just pick one of these members, okay, if A is in W, then A is equal to the A transpose. And you see, if you have alpha times A transpose, 2, 3, 4, 5, 6, remember, this is alpha times A transpose. But A transpose is the same as the A, so that give alpha A. So what do you prove? You prove that the alpha A is also symmetric. So alpha times A is in W. So W is closed under addition and the scalar multiplication. So W is a subspace. Is a subspace of, that's a subspace of all the 2 by 2 matrices. Because the other 8 condition automatically would satisfy because they are matrices. But the main part is if it's closed under addition and the scalar multiplication by itself. Okay, so you may think that all of them are the same, but this is going to be, I give you a remark and then I give you the next one. You see, this remark is very important, very helpful. Remark, see, if W is a subspace of V, okay, then look at this one. Then for any, let's say U in W, okay, U plus negative U. Remember, this sum must be in W is equal to the 0 is in W. So that will help you quite a lot. So if the set is going to be a subspace, that set must contain 0. Okay, 0 is in V. And now we prove that 0 is also in W. Okay, so this is going to be the case. So if W is a subspace, then 0 must be in W. That will help you quite a lot. Sometimes they give you a subspace and they ask you whether, okay, they give you a set and they ask you whether this is going to be a subspace. So we can use this fact quickly to take care of it. And we have it quite a lot. So you have these type of problems in your book. Example, they ask you which of the following. Okay, which of these, okay, the following two sets, which of these two sets, okay, or two subsets is a subspace, is going to be a subspace, is going to be a subspace of R2. Okay, you want to check it, and you have quite a lot. Part 1, this is it. They give you something, we call it W1, is going to be X comma Y with the condition that they satisfy this condition, X plus 2Y equal to 0. That's the first one. The second one, the members are X comma Y with the condition that X plus 2Y is equal to 1. See, you consider all the points that satisfy this condition, and you want to see if this is going to be a subspace, or the second one. You see, first thing to do is look at this one. If the W1 or W2 happen to be a subspace, they must contain 0. So you check 0, 0 here. 0, 0, 0, 0. It's satisfied. So the 0 is in this one. It doesn't mean that you are done. This means there is a possibility that the W1 is a subspace. Look at this one. 0, 0. If you put X equal to 0 and Y equal to 0, that gives you 0 equal to 1, which is impossible. So this means W2 over here does not contain 0. So W2 is not a subspace. You reject it right away. Okay, so that's very helpful to know. Very helpful to know. First thing to do, especially when a group of them are going to be given to you. And if you want to see if there is a possibility that you will get a subspace, the first thing to do is just check 0, 0s. 0, 0 is not in this one. So this is not going to be a subspace. But this one may be. So that's why we are going to know. We are going to check it. Okay. So this is how we're going to check. Solution. So you can simplify this one a little bit to identify which type of elements do you have. You see the W1. It's like, X plus 2Y equal to 0 is like one equation. If you want to solve it for X and the Y, you have to pick, one free agent if you like. So what we're going to do is, this is it. So for the W1, this is it. So let Y, for example, to be equal to the T. So this is it, you see. Note that if X plus Y equal to the Y equal to the 0, then X would be negative 2Y. That's a relationship. You can simplify it. So let Y to be equal to the T, then X would be equal to the negative 2T. So that would be easier for you to handle the members of the W1. So your W1 is of this format. W1 is the point of the form negative 2T and the T for any real T. Okay, this is it where T is a number, is a real number. Now it's easier to check those two conditions. Okay, this is the way we do it, because you have a point with this relation. That would be not easy to prove it. So we just, it's a equation in two variables. So you just move the 2y to the other side. So y is going to be a free agent if you like. So now we can check this one quickly to see if it is going to be the, okay, if this is going to be a vector space. So just condition one, pick two members. You see one member, you call it the negative 2t1 and the t1, plus another member, you call it negative t2, comma t2. If you add them together, the first part would be negative t1 minus 2t2. And on the other side, we get the t1 plus t2. Okay, so if we keep going, we can factor out the negative sign here, negative 2. So the result would be t1 plus t2, comma, and that's a t1 plus t2. You see, you get the same type of members. We can call this one t3 if you like. It's a negative 2, 3, and the t3. You see, it's the same kind of members. You see the members, negative 2t, t. These are the members of the W1. So we add two of these members and we get the same one. So this means is in W1. Because you have to prove that if we add two members of your set, you get a similar members, which is going to be, okay, a similar member. Okay, that's the first condition. The second condition, if you multiply a scalar, that would be easy. Okay, so I'm going to show that one too. So the second condition, to have a subspace, okay, if you multiply alpha times the member of your set at 2t and the t, so it's going to be negative 2 alpha t and the alpha t. It's the same type of members. Okay, because you know you can call this one again. You see, you may call it the negative 2 t1 comma t1 is in W1. Okay, if you multiply by a number, you must get something similar. It is something similar. You see, your set is of the form of negative 2tt. Whatever it is here, it must be repeated. So the W1 is a subspace. W1 is going to be a subspace. Okay, subspace of R2. Okay, so this is W1. The W2, as we talk about it, you reject it right away. W2 is not a subspace, not a subspace. Why? Remember the condition that you need to check is, okay, x plus 2y is not equal to the, okay, because 0 equal to the 0, 0 AC is not in W2, because you're going to have the x plus 2y equal to 1. If you substitute that, give you 0 plus 2 times 0 equal to the 1. So 0 equal to the 1, which is not possible. So anytime you want to reject, this is the type of ideas that you are going to know, you're going to have. Okay, so that give you the idea of the subspace, which is very important sets. Okay, and so the space is big. If you want to work with a space, is going to be a very okay, it's going to be a very big one. So what we do is we are going to shrink it, and we're going to consider a subspace. A subspace is exactly the same as a set. So if you pick two members in the subspace, if you add them together, the addition is always in the bigger sets. But if it's going to be inside the smaller set, we say, oh, this is going to be a subspace. Okay. So now what we do, we start working in some other operation with the subspace. Okay. So it's very important to get a good idea of what is going on in your space to be able to consider some subspaces. Now, we are going to have some other subspaces. I'm going to introduce at least one more for you. We have something, we call it a linear combination of vectors in a vector space. That would be helpful for us. Okay, so these are going to be the examples of the space, vector space, subspaces. Let's talk about this expression too. What's going to be linear combination? Okay, we do quite a lot of this type of ideas. What is linear combinations? Combinations of vectors. Okay, of vectors in a vector space. In a vector space V. Remember, we have two types of operation only: addition, vector addition, and scalar multiplication. Now, what is this one? You see, suppose V is a vector space. Suppose V is a vector space. You know what does it mean? There are some objects, we call them vectors, and there is the addition and the scalar multiplications. Now, a vector, okay, a vector V, lowercase v, okay, in V is called a linear combination. A linear combination. Linear combination of some vectors, of vectors like u1, u2, u3 up to the, let's say, un. Okay, un in our vector space. It's a linear combination. It can be written in this format. When the vector v is going to be something like, c1, u1, c2, u2 up to the cn, un, where these c1, c2 up to the cn are numbers, are scalars. Okay, so when we say a vector is a linear combination of the other one, this means I can find some numbers. I can find some numbers, c1, c2 up to the cn, so that I can write the v as a linear combination of u1, u2 to the un. Remember, the only operation that we have is addition, plus, plus, plus. Okay, and a scalar multiplication. A scalar, you see, c1 is a number. 2u1 plus 3u2 plus 5v3. So these are the only operation that you have. So when say is a linear combination, means you can produce, you can generate your vectors. So your job is just to find this type of linear combination. Give you an example first. So look at this example. The example is going to be, so suppose we are in R3. Okay, so this is going to be a subspace, or let's introduce this one. Okay, so suppose the vector space in question is R3. Okay, and we have three vectors. Okay, so let's call it, this is a set S, consists of these three vectors: 1, 3, 1. 0, 1, 2, and you have 1, 0, negative 3. Okay, these are going to be the one. Okay, I'm going to call this one, let's say this is going to be something like V1, this is going to be something like the V2, and this is going to be something like a V3. Okay, if this is going to be the case, then, for example, we can arrange it so that the V1 is going to be a linear combination, is a linear, okay, it's going to be a linear combination of the other two, okay, of V2 and V3. So this means I can write the V1 as a number times V2 and a number times V3. And this is going to be the case. The suggestion is V1. It can be written as 3V2 plus V3. You can check it. You see the V1 is 1, 3, 1. And it's going to be 3 times V2, 0, 1, 2, plus the V3, 1, 0, negative 3. You see, check. The first component, 3 times 0 would be 0, plus 1. The second component, 3 times 1 is going to be 3, and 0 is 3. The third one, 3 times 2, 6. 6 minus 3 would be, okay, 3 times 2 would be 6. I'm sorry, this must be a negative 5. Otherwise, it's not working. Suppose this is a negative 5. Now this is going to be a negative 5. Now that would be fine. 3 times 2 would be 6. 6 minus 5 would be 1. So as you can see, the V1 is a linear combination of the V2 and V3. Okay, now your job, we give you these vectors and we ask you to find these numbers for us. 3 and the 2, you do quite a lot in this chapter. So I want you to see at least one of them tonight. Okay, so this is your job for the line time, if you like, in this section. Let's get one of them, and you will see one in your next quiz. So what's going to be the example? There you are. We are going to ask you to write. Okay, write the vector. Write the vector. Okay, this is it. We'd like to write the vector V, which is going to be equal to the 1, 1, 1 as a linear combination. As a linear combination. Okay, as a linear combination of these vectors. Of vectors, and this is it. We have 1, 2, 3, comma, 0, 1, 2, comma, negative 1, 0, 1 in R3. Okay, that's it. So a vector is given to 1, 1, 1. We want to show that, or to write V as a linear combination of these vectors. So this is what we do. Solution. So one should find, or we should find, one should find 3 numbers, scalars, C1, C2, and C3, such that, there you are. such that this vector 1, 1, 1 is equal to C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 1, 0, 1. This is your job. There are different ways to do it. It's just the beginning. So we are going to multiply this inside, and then we let them to be equal to each other. That gives a system of 3 equation 3 variables. You solve it. If you can solve that system, you're done. You get the C1, C2, C3. Otherwise, it's not. Okay. So this is going to be the case. So the situation is going to be, so we have the 1, 1, 1 is equal to, you see the inside, the first component, C1, C2, C3. So this is the first one I show you. So it's going to be C1, 2, C2, 1, and the 3C1. We do it right away, of course. You just multiply this one. That gives you 0, C1, 2, C2, sorry, C2. And you multiply this one, that gives you negative C3, 0, C3. Okay, now the components together. So it's going to be equal to, so that gives you C1, this is 0, minus C3, comma, that gives you 2C1 plus C2, this is 0, and the third component that says 3C1, 2C2, and the C3. You see that's going to be the 1, 1, 1, 1. I'll let them to be equal to each other. You see each component and make this system of the equation. Again, in future it's going to be simplified, but not now. It's a 2C1 plus C2 equal to 1. And the last one is a 3C1 plus 2C2 plus C3 equal to 1. Okay, this is going to be a system of the 3 equation 3 variables. Sometimes it's easy to solve it right away, or other times you just use the matrix form to take care of it. Okay, so the matrix form is going to be what? This is C1, there is no C2, that's going to be augmented matrix, 0, negative 1, 1. The second one is going to be 2, 1, 0, that give you 1. And this third one is going to be 3, 2, 1, 1. See, this is going to be your matrix. So quickly, you can change it to the echelon form if you like. See, this is it. R2 into the R2 minus 2R1, and this is R3 into the R3 minus 2R, okay, R1 again. So the situation is the first one is unchanged, 1, 0, negative 1 and 1. The second one, R2 minus 2R1, that gives 0. Okay, minus 2R1 is going to be 1. 2R1, that gives you 2. And the 2R1, that gives you negative 1. Okay, and this is R3 minus 2R1 minus 3R1. So that gives you 0. 3R1, that gives you 2. Okay, 3R1, that make it into the 4. And the 3R1, that gives us a negative 2. You see that's going to be the 1. And quickly you see that they are the same. So this is it. If we get the R2 minus R2 minus 2R3, this would be 0, and then be able to do it right away. Okay, so it's going to be 1, 0, negative 1, 1, and this is going to be 0, 1, 2. Again, there are some other easy way to do it. Okay, so this is going to be 0, 0, 0, 0. So the system would have, Okay, so the system would have infinitely many solutions. So the last, you have to pick the C3 to be, okay, you pick the C3 to be free is equal to the T. So from here, this is the T2, okay? So that gives you, it's a C2 plus 2C3 equal to the -1. Okay, so that gives you the C1, which is 1 minus 2T because of the C3 here. Okay, and the first one, and that gives you C1 minus C3 equal to the 1. So the C1 minus T equal to 1. So the C1 would be 1 plus T. Okay, so this is a situation you're going to have. So basically what you have is that I already got the C1. So C3 equal to the T, okay? The C1 is equal to the 1 plus T, and this must be a C2, yes? That's a C2, of course, C2. And this is going to be the C2. Okay, so basically what we have, I put it over here. Okay, so I have my C1, which is equal to the 1 plus T, and I have the C2. And sometimes it's easier to solve it just right away. But we are going to have some other easiest method in future. Okay, this is it. But remember, you need only one number. You pick a T equal to 1, for example. So that gives you a C1 equal to 2, C2 equal to the -1, and the C3 equal to 1. So you are able to find some numbers. So your vector is going to be a linear combination of these three vectors, okay? So if you call the original vector V, so this is going to be 2V1 minus V2 plus V3. This is going to be a linear combination of those three vectors that is given to you. So you are going to do these type of operations quite a lot for us. So get used to it, okay? Sometimes it's not going to be possible to find, okay, these type of vectors. It depends on the outcome that you're going to get here. Okay, so I just explained it again. So that's it. And we be given a vector that's 1, 1, 1. We want to write on the linear combination of the three given vectors. So that's it. So the linear combination means C1, C2, and C3. You put them together, simplify it. Eventually, we get this matrix. It would be in future easy to find it. Look at this one. 1, 2, 3, 1, 2, 3, 0, 1, 2, 0, 1, 2. Okay, but it's just the beginning. We don't want to, okay, to jump if you like. But we are going to get to those, those cases that will make it easy to find out. Okay, but not now. So in this case, it was possible to find, but you may not be able to do it. Okay, I just give you a similar one so you know that, because you have them in your book, and we give you a couple of them. Just one question of this on your next quiz. So they ask you to see if it's possible. If possible, okay, we want to do the same thing with this one. Write, okay, write the vector. Okay, the vector, they call it W, equal to the 1, -2, 2 as a linear combination. Has a linear combination of the same vectors that we have in the previous one. I want to do this one in the shorter form so that you know how we do it. So that's a 1, 2, 3. That was a 0, 1, 2. Okay, and the last one was -1, 0 and 1. Okay, the similar one for this one. So we can do it quickly, see when or how you may get a negative answer. So there you are. So the W, this is it. So you want the W 1, -2, 2. This is going to be C1, 1, 2, 3. Okay, plus C2, 0, 1, 2. And the C3 that give you a -1. Okay, that give you a -1, 0, and 1. So quickly we can simplify it. So this is going to be C1, the first component, nothing here, and this is a -C3. The second one, 2C1 plus C2, nothing here because this is 0. And the last one, 3C1, 2C2, and the C3. You see, this is going to be your vectors. Put them together to get that system of the equation. So you have the C1 minus C3 equal to 1. You have 2C1 plus C2 equal to the -2. And the last one, 3C1, 2C2 plus C3 equal to 2 this time. So quickly, we put them together. That's the given vector, and these are going to be the one that are going to be generator, if you like. So again, you can try to solve this system of the equation manually if you like, or quickly at augmented matrix. C1 is a 1, there is no C2, then a -1 and 1. The second one, this is a 2, 1, no C3, -2. Okay, and the last one is going to be 3, 2, 1, and 2. Okay, this is going to be your matrix. You do those operations that we did again quickly. So the R2 would be R2 minus 2 R1, and the R3 would be R3 minus 3 R1. Okay, so that would simplify. It's going to be 1, 0, -1, and 1. Okay, so that make it to the 0, 1, -2, so that give you a +2, and the -2, -4. Over here, R3 minus 3 R1, 0, 2, 3 R1 that make it to the 4, 3 R1 that give you a -1. You see, look at this one this time. So if you do the same thing that you did for the other one, that give you R3 minus 2 R2, you arrive at the contradiction right away. So that give you 1, 0, -1, 1. And that's going to be 0, 1, 2, -4. R3 minus 2 R1, 0, 0, 0. Okay, -2. That give you what? +8, 7 in this case. Okay, because that's it. And that 4 will disappear. Okay, and -2 that give you 8, and this is going to be 7. You know that this is impossible. We cannot solve this part. So it's not possible. So W is not, or it cannot be written, is not a linear combination. Linear combination of those vectors of V1, V2 and V3. So it's not the case that you always will find this type of linear combination for yourself. Okay, so this techniques is going to be used quite a lot. I think that would be enough for this time. We are not done with this 4.2. It's a very important section. Then this linear combination is going to be very important for us. We are going to check to see if we can find a set of vectors that give us all the vectors in the subspace. This means we can find any vectors as a linear combination of the others. Okay, and that set is going to be very important for us. We call it the basis. So we are going to continue. I will post another one for you by Friday, so that get the section 4.2 and 4.3 to just keep you moving. These sections are very dense. So if you go with the 2 or 3 sections per week, that would be fine for us, because the chapter 4 is very dense. So I give you quite a lot help, so that we able to get through it. It's a very important section of the course. Okay, so that's it. Just check this one. Any question, let me know. I try to just get your test to see what's going on. Any difficulty, anything you want to meet me, just send me an email and we can fix it for you. Okay, have a good one and take care. We continue with this one. Just make sure to get a good understanding of a definition of a subspace, because that would be very crucial for the rest of the course. And these examples that I gave, just check them. I post your next practice quiz so that you get the idea. You get quite a lot of this idea of the subspaces and the vector spaces on that, that practice quiz. Okay, have a good one. Take care. Bye.